So before coming to the interpretive part, so we have to basically see to generalize a general formalism of how we can mathematically formulate quantum mechanics in a language, uh, in a mathematical language. The formal aspects of quantum mechanics, how we can express them in a mathematical language, so that at the end we can relate it with the interpretive part of that entire thing. So it's we're coming to the part. To the first part was bit how we studied the experimental, how the states, whether it was corpuscular interpretation, the wave interpretation, and the causal anomalies, and how we can account or do away with those causal anomalies in terms of different interpretations, which were primarily three. One was exhaustive interpretation, the other was restrictive interpretation, and the third one, which included, was where we sort of said we had an interpretation which was where we use the logic, where the indeterminate thing, indeterminate as a quantity was not it was given some meaning or value. So continuing with that, before we are going to come to the interpretive part of it, so we are this part is how we can outlines of mathematics, or quantum mechanics, or the formal aspects of quantum mechanics when expressed in the way in the mathematical formalism. So we come, first of all, we have to see the expansion of a function in terms of orthogonal set. So normally in mathematics we normally talk of square integrable functions. When you talk of psi, and we relate psi as a complex function, such that the probability as such cannot be. Probability is not an defined. It's not a complex quantity. We define probability in terms of something real. So a psi square or psi star becomes it becomes meaningful in terms of defining probabilities. So the complexification of the wave function is a mathematical requirement which has been there, and whether we have psi star psi will which gives a square of the amplitude, it's going to express that complex wave. Yes, that's it. And when we talk of this expansion, it's in terms of some expansion function psi in terms of C1. So we basically talk of we have a function, a function psi x can be or is expanding. So another thing which I want to mention is this psi square. It should have some convergence properties. So which are the convergence properties? For this expansion psi star, so which we are going to integrate. So it may be a mathematically which are the sequences which are going to converge. So it's also an important mathematical function, mathematical exercise, which convergence sequences or which sequences are going to converge in a general integrable function. But since here we are interested in expressing psi square, this wave function, in terms of some expansion, it should have some convergence properties, which normally we see it in terms of L square, square integrable spaces, which should converge. So before how that thing we incorporate, we'll say a function psi x is expanded in terms of the set pi x within a domain d of x if within d the relation holds. The relation is psi of x is basically sigma I phi of x. Here I can be basically 1 to I can go to infinity. And the expansion coefficients, so we have a psi, we define it in terms of sigma I phi I. Here sigma I are the expansion coefficients, and sigma expansion coefficient, sigma I are constants, and they do not depend upon x. They do not depend upon x for every function phi of x. So this is the thing. So there is a particular constant sigma I. That's fine. Now, when is this function complete? That's the thing. When is the function complete? In the expansion of this thing, such that for the two relations should hold. These are sigma I is so for this function to be complete, we are imposing two more conditions which should hold. Then we define this sigma I can also be defined as psi of x phi I star x dx, such that so for it to be complete, we define sigma I can further, this expansion quotient can further be defined as this psi of x or phi of this thing, such that if you integrate both of them, or you multiply psi star psi with psi of this psi star this, and you see from this you can have this condition, psi of x square can be equivalent to sigma of I x square. How we can see it from this? If you have psi star psi is psi square, and you have phi in terms of psi I, sigma I in terms of phi I, so you can have psi star is equivalent to so you leave it. So we say that this is relation 2 and this is relation 3. So if we impose these two conditions, then and this integration into extends over the domain D. So we talked of a domain D of X. If D holds, if D should hold this relationship. So if a condition, so now we come to orthogonality. A set of functions, phi ix, for which every pair of psi of x and sigma I is connected by 1. So if this and this is connected to this, then if psi I is connected to this 1 and it satisfies the relation this and this. So now the question is, so if you have defined psi I in terms of expansion coefficient of sigma into phi x, such that this expansion doesn't depend upon x, and we define psi I like this, and we impose this condition, then a set of function phi x for which every pair of psi x is connected by 1, so it is known as its. So if this satisfies these two conditions, then we say what? We say that it's an orthogonal function, is called orthogonal. And it's also normalized. And further, it's also called quadratically integrable. Another term. So we can integrate it quadratically. So for the case of D being so normalization finds its expression in this equation. This is the normalization thing. And for it to be for it to hold these convergence properties, this expansion, this should come out to be finite. This should come out to be finite. And further, if it comes out to be finite, it should hold some convergence properties for given sequences. And the sequences are defined as an expansion of psi in terms of sigma I phi I. So if it's not, so it becomes another task. If the functions they don't have convergence properties or not, and whether they can then be integrable or not. So it becomes a larger mathematical question. So it's a separate discussion. So now the question is. The question is whether conditions of orthogonality and normalization. So we have imposed the condition of this orthogonality and normalization. Orthogonality and normalization. What do you mean by that? Can be expressed by a direct formulation. So in terms of these functions only, in terms of these functions alone. Without reference to other functions. So can we do it? So in that case, orthogonality and this thing can be defined as we can define these conditions into phi of x, phi k star x dx is delta ik. So we have here a real star symbol, and sometimes it's also Kronecker symbol. We define it as, so here the book has termed it as Weierstrass symbol. Sometimes also, or mostly talked in terms of Kronecker symbol, where delta ik is defined such that if I is equal to k, it's 1. And if I is not equivalent to k, for other values of this thing. So for other values, we have a condition of orthogonality. Orthogonality means when I and k are same, and when I and k are not same, that's it. So it's easy to show that. That if psi of x, which was our first, the way we defined it, psi in terms of phi of x. So if it's first, second, if this first and fourth hold, if first and it's fourth, equation fourth, if this and this will hold, then what? The relations 2 and 3 will also hold. Relation 2 and 3 will also hold psi of x. So initially we impose those conditions. And the way we defined a condition for being orthogonal, and we define this function to be orthogonal and normalized if it satisfies this and this. So this was imposed. Now what we are showing that if this and this holds, then relations 2 and 3 can be derivable. Relations 2 and 3 can be derivable. So if this and this holds, so earlier the justification part was why should we define it this way? Why should we say that if this function can be orthogonal and normalized if we define things in this and this way? The justification was not there. Now if we impose another condition, if we define psi in terms of this Kronecker thing, if we impose this orthogonality condition, then we can derive this and this. That justification, a priori justification can be justified. That can be justified. How? So we compare. So we see. So what we can do is multiplying equation 1 by phi I star. So we'll see, this is psi, we multiply it by phi I star, equation 1. So it will come out to be psi of x is our own, psi of x, phi I star x. So we have multiplied it by phi I star. So it will be equivalent to phi k star x sigma I phi of I x d of x. So it's like this. Psi I phi I x is equal, that's fine. Psi of phi of x is equal to, you can see it, integral of phi of star. So we have multiplied phi star this left side and right side, and integrating both sides we can get this equation. And further you can see, further we can see we can see it here, we can see it here, we can see it here. So it will come out to be, we will get sigma out, sigma I phi I star x phi I k star x dx. So you can say sigma I, again this phi I k phi I star phi I k phi I star in terms of canonical delta, it will be 1 or 0, depends how we define these subscripts I and k. So we can have phi I star, so it's basically it's sigma here, I and k. Now you can have it sigma, we have kept it phi of x, phi of k star. Physics student. So what we have done is basically you can define this, how we define a normalized condition, how we define normalized wave function. So we initially try to say, define things in terms of psi and phi, and if we have this psi, we define psi as an expansion quotient sigma I phi I x. And from this we impose two conditions. We further define this sigma in terms of psi I phi I, and we impose this condition psi of x square is equal to sigma square integrability condition is there. So we don't have justification for this. We don't have. So further, what we are going to say that if we define sigma in terms of this equation, if we multiply this by sigma I star and this by we multiply both sides by phi I star, we can have the justification why we have imposed this condition, by which we make this function as orthogonal and normalized. So what our aim is, how we can, the justification of normalizability and orthogonality, how we can derive that justification. We did a mathematical trick, is we multiply both sides by psi phi I, and so we'll see. So it will, so further what comes to our rescue, something the way we define Weierstrass function or Kronecker delta function, where delta I is, if I is equal to k, if I is not equal to k, 0. So if we see this impose here, this psi is an expansion quotient of phi, sigma I phi I. But further we have multiplied both sides by phi I star. Now phi I star and phi k star. If I is equal to k, it's 1. If I is not equal to k, it's 0. So in the sense you can say the wave function psi, there can be all number of states, the orthogonal states and orthonormal, which states will not contribute and which states will contribute. For this particular combination, these states will contribute and they will not contribute. And this mathematically, this can be represented as sigma I delta ik. So we write this phi I star phi I k as delta ik. So if it's delta I is equivalent to k, it's 1. If I is not equivalent to k, it's 0. So we can write it. If I is equivalent to k, it's sigma k. So this is one condition which we assumed. Why should we impose this condition on this? We assumed this. We initially defined psi I like this. Then we impose two conditions: this condition and this condition, for it to be orthogonal and normalized. But why we did not say why we should impose this condition? We take it like that. But further, if we define psi I in terms of we multiply it both sides by this, we arrive at this condition, the first condition. Its justification is there. Okay, this one. Now we have to see how we can arrive at the second condition. So similarly, we can say to show the second condition can also be arrived at, what we are going to do is integral of psi of x square dx is, so if it's psi of x square, because it's a probability wave, probability doesn't have a real value, probability has a real value. So but we have defined psi as a complex wave, psi. So psi complex wave will not have real probability. So that's why we have psi square. So we can have psi square like this. But now psi we have defined in terms of, psi will define here in terms of sigma I, phi I, sigma I, phi I. So we'll have, so we'll just first psi x square can be written as psi of x, psi star x. We can write it like this. And further, we can write it as sigma I phi of I x. This is I, this is k. Sigma k star phi. This is fine. So we actually first condition we have shown. These two are conditions for orthogonality, provided we define psi in terms of as an expansion coefficient of sigma I phi. The first orthogonality, why should we impose this orthogonality? We have seen it from the first. Now we are going to show the second part of it. So again, we define psi square as psi star psi, or it will be, now we are going to abnormal, this one, we are going to just put it here. So for psi, we have sigma I phi I. For psi star, sigma star. Now we are going to rearrange. We are going to rearrange in that sense. So we'll take this. These are constants. We have defined these as sigma I are some sort of constants. Its value doesn't depend upon x here. Okay. So we'll get sigma I and sigma k star in the left hand side, and sigma I, sigma k, it's sigma I, sigma k star in terms of phi I x and phi k x star dx. Again, if I is equal to k, will come, then it's 1. If I is not k, is equal to 0. So if I is equal to k, you can have this condition can be further sigma I, sigma k is sigma I star. Sigma I, sigma k star. It's delta I into the conical delta. If I is equal to k, it's 0. If I is not k, is equal to 0. Or if I is equal to k, then it will be sigma I square. है ना, and it will be 1. I is equivalent, it will be sigma I square. Delta I is equivalent to, it will be equivalent to 1 multiplied by 1 is. So we have arrived at, we have arrived at the second integrability condition, this one. So the thing which we want.
Is this condition proposed by math or it's just physics there?
It's a good question, whether it's imposed by. So what we are going to see is further, in mathematics there are some sequences which are convergent and some sequences which are divergent. Here we assume that this expansion coefficient, if you define psi this way, this sequence at the end should converge. It should have some real value. Just we say psi square alpha 1 x1. At the end we say probability is 1. It will have some. So it's going to converge to some finite value. And we impose this condition. So those integrals which have this property, we assume they are square integrable functions. They should have a finite, they should have convergence property. It's not necessarily all the expansion coefficients should have those property mathematically. There can be some functions which will not have convergence property. They may diverge or they may be 0 or whatever, the sequence at the end, when we sum the sequence. It will not necessarily converge. But we are interested in the wave expansion coefficient of the wave function psi. It should, we impose the condition, it should have some convergence, which value should be finite at the end, and we sum the total contribution of the wave function psi. So those functions, we are narrowing the mathematical definition to the physical definition in terms of how the physics of wave function is to be taken. It can make sense. Otherwise also it can, those non-convergent functions can also make sense, but they will have a mathematical sense. Or they may have any other sense. In terms of physics part of it, if we impose a condition that wave function, the total contribution of the wave function should have some finite value, we assume that they should have convergence properties. And we say they are square integrable functions. Square integrable in the sense because psi square, we have square integrable functions. It's defined that way, square of the function. So if they have convergence properties, provided we assume that if we define it this way, we should have this. This should be defined. If we define things this way, then only it will be orthogonal and normal. So initially we did not have why should we define this in this way. Then what we did, we tried to define psi in terms of this and phi in terms of. We first step, what we did, we multiplied it by psi I, and we saw this condition is satisfied. In the second way, we defined psi square, integration of psi square, we arrived at this second condition. So
when we solve 1D potential, we get those solutions then.
So we come to those solutions, how we arrive at that. That's another question. The solution of Schrodinger equation. You are coming before it. Once we come there, we address that question. In the first case, we are going to define how we define things. They should be square integrable. It should have convergence property. And if psi is defined as an expansion coefficient of sigma I, phi I, and we impose these two conditions, and from the orthonormality and this thing, if we define this Kronecker delta, we can arrive at these conditions like this. We can have justification of these two conditions also from this simple exercise. We multiply it by psi star, and we can arrive at this thing. This is it. And further, if I'll say like this, if I'll say. So I do not see it there. Phi I x, phi k x dx is 1 and 0, phi I x and phi k star dx is k not equivalent to iota. For k is equal to iota is 1 and it's 1. That's it. These are sometimes also known as so these are also known as sometimes reflexive. In mathematics, we call them as reflexive functions, which are हाँ we just had this thing. इसका हमने थोड़ा सा because in the next we are going to start it the next इसका in the detailed sense. And one small thing which I want to add to it is that whether, because we are interested in the eigenvalue and the eigenstates, which I am repeating, and basically normally we you imagine eigenvalues as some solution of an equation, linear equation normally, है ना? जैसे linear equation है ना, a1x plus a2y, इस तरह a2x a1 a2x to a3x3 is equal to 0. How we solve linear equations? The way we define augmented matrix, whether it has a trivial solution, non-trivial solution, है ना? So, but here we are relating the eigenstates with the eigenvalues, and different eigenstates can have same eigenvalue. So the thing is that thing. So that's why we are going through entire this exercise: orthonormality, orthogonality, Kronecker delta, and how we define psi in terms of phi. It should impose these conditions of orthogonality and normalization. Because we are basically at the end interested in trying to arrive at the eigenvalue of the eigenstates. So further we can say whether these functions are orthogonal or they are orthonormal or they are normalized. They require a special analysis, mathematical analysis. For example, if we define a function if we define a function phi I like this, phi of kx is equal to 1 by root of 2 pi e to the power. So it will, this function, this e, a domain should extend between 0 to 2 pi. Because why? This is, if you define e to the power iota x, it's cos of x plus iota sine. So sine will be sine 0 to pi. Cos will be maximum from pi by 2 to 2 pi by 2, 3 pi by 2. So in the same way, you have to define this, where the value of the function, where it will be maximum or where it will be. So that's why in this function, the way when we define psi and this, we are also interested in the domain of the function. How this x, how we define domain, which range of values or which sequence of values it's going to map upon. This state psi, which sort of values, it will know whether it will take all values or which sort of values it is going to exhaust. So we'll have some mapping to normal functions as a trigonometric function. So that's why the thing which we study them is we define study them in terms of Fourier expansions. Fourier expansion. Initially, I did not say why we are using. We said only one thing, that we studied K space and P space. We define this site in momentum space as well as in position space, and we could define, we can go from position to momentum space. But there is another, we have Fourier analysis, how we are going to integrate these complex waves, total sum, the contribution. So we have such that, for example, this phi x can be defined as solutions of differential equations. Solutions of, so how does it come different? Because we have defined Schrodinger equation as time dependent or time, they are second order partial differential equations. So on left hand side there is psi and right hand side there is energy. H psi is going to E psi. Now we are going to find eigenstates and eigenvalues in those differential equations. But those have to be seen in terms of Fourier expansion of solution of differential equations. And in those solutions, you can have, and they are called the eigenfunctions. They are called those solutions of the eigenfunctions of those differential equations, which will give what value they will correspond. In a sense, what value this wave function psi will take. We are going to integrate along all the expansions, sigma 1, phi 1, sigma 2, phi 2, and c. And the wave should be normalized and it should be also orthogonal also. These are the conditions we are going to impose. Yes. So this much we have done. Stop. Okay, that's fine.